Today is the last lecture on the things that are supposed to be covered in the syllabus. So we are going to talk about the observer-based dynamic controllers. That's the name of the section. This is section 9.4. Observer-based controller design or dynamic controllers. Okay, so let's go back to 1950s. I have a rocket. I want to send that rocket to moon. I have it just turns out that I cannot measure all the states of the rocket. I have a bunch of pitot tubes all over the rocket. I have a bunch of attitude sensors on the rocket. So I'm able to collect some information on the rocket, but not all the states of the system. So I now need to run an observer. And what we have done so far is we have figured out how to design a controller if we had full state measurement, if I can observe all the states at all times. And what we have learned is how to build an observer of the system. So somebody has given me the control action. I'm going to apply that control action. I'm making the measurement. From the measurement, I want to infer what the state of the system looks like. And so those two problems are done. So I have done I'm making all the observations. I know how to design ut as a function of xt, right? So this is something that we know. This is known as a control law. I want to make one specific note here. Generally speaking, many books or many references or many papers would use u of xt, u of t, and then u. I absolutely hate that notation. And the reason why I hate the notation is that the operator u gets overloaded multiple times. So that's why I tend to use mu or pi or something to demonstrate the control law, which takes as input xt and gives it as output ut. Okay, so that's why I use this notation mu. And if you are if I'm in your qualifying exam or candidacy exam and I see that you are overloading this notation u, I'm going to be very angry. Okay. All right. So even if you're writing papers, make sure that you distinguish between the control law and the control action. The control law maps state to action, but the action is u of t. Okay. So action is separate from control law. So if I'm making the full state measurement, I know exactly how to compute the control law. I know how to do pole placement. I know how to do eigenvector placement. And I know all sorts of Python packages and MATLAB packages that will help me do that. The second part that I know is if you give me the measurement, I can figure out so if you give me this this system, I know ut, I know yt, I'm able to measure I can see the measurement, I can store it in the memory. I can figure out an estimator x hat of t such that xt minus x hat of t goes to 0 as t goes to infinity. right? And this was the subject, this was the topic of study in the previous class. Now go back to 1950. I want to design a controller for this particular system. Now the question is, find a stabilizing controller for x dot t equals to axt plus but, yt equals to cxt plus dut. I'm merging the two problems. This was the control design. This was the observer design. And now I'm trying to do something which is more complicated than individual subpart. Okay, so what would you do? What would your line of attack be in 1950? You are responsible for sending a man to the moon. You are given this rocket. Somebody gave you this ABCD matrices, and now you are responsible for that astronaut's life. That astronaut's life is in your hand. And how will that astronaut be alive? If you build a stabilizing controller. If it's an unstable controller, the rocket is going to blow up, and many astronauts have lost their lives because of that, because of non-stabilizing controllers. But your goal is to come up with a stabilizing controller. So you have a lot of responsibility on your shoulder. So what would your line of attack be? How would you do it? What's your step one? Step one, step two, step three. 3 steps to success. What is my mu of? I don't even have x of t now. I have mu of yt, ut, sorry, y tau, u tau, tau less than equal to t. I have all of this information in my arsenal. I have like a huge hard drive. I'm storing all the observations and all the actions in that hard drive. And I'm supposed to come up with u of t using all this information. That's my goal. It sounds like a very difficult problem, okay? And it is a difficult problem until we simplify it. But I want to hear your thoughts. What do you think? How will you design this mu? Yeah, go ahead.
First step, understanding which states are controllable and observable.
Right. So assume that things are controllable and observable for now. We'll go for the more complicated case slightly later in the class. So for now, just assume that things are observable and controllable. So assume observable and controllable system. What is my step one? Yes, please.
Step one would be finding your X hat to try and build something that we can use.
Okay.
Easier to control when we assume we know all of this
Okay.
information.
Wonderful. So design observer. To get x hat of t. What is step two? So I got x hat of t, knowing very well that this x hat of t might be very far away from x of t in the beginning of the time. So first 10 minutes, 15 minutes, 1 hour, 10 hours, my x hat t will not be the same as x of t. I'm admitting that fact at the very beginning, at step 1. What is step 2? I want to find a stabilizing controller. If you don't come up with step 2, an astronaut is going to die. So I have to force you to think about what step 2 should be.
Using that X hat to find the pole place controller.
Okay, so design F such that A plus BF has desirable property. So it could be pole placement, it could be eigenvector placement, whatever, right? So find a stabilizing controller F. What else? What is step 3? I still don't have my mu. I want u of t equals to something. What is that something going to be? Yeah. Sorry? X, I don't know what X is.
Then you use like
The estimated thing. So my mu of, well, I guess my u of t will be mu of x hat t, which will be fx hat t. Is that what you are suggesting? Yeah.
And as you mentioned before, potentially there might need to be an offset factor, a fudge factor, for lack of a better word, for when x hat t is not yet converged to x t.
So I know that it will converge eventually, but I don't know at the beginning whether it's close to xt or not. So if you put an offset factor, how do you determine what that offset factor is going to be? That's the issue, right? Should it be +1 or should it be -1 or should it be 0? Like right now the offset factor is 0, but I know that we are sort of in a deterministic situation, so it's all mean 0 and all that stuff. But yeah, if you have non-zero mean, then you might want to put some reasonable offset factor. Okay. So what you have done here, what the 3-step process looks like is you first design the observer separately from designing the controller, and then you merge the two things. Okay, you merge the observer with the controller that you design. So this one is assuming that you have the full state feedback. So this is the full state feedback, and you're designing this F assuming that you have a full state feedback, but because you don't have the state, you substitute x hat of t, which is the estimate of the state, in your controller. And now our goal is to prove, so that was the question. Now my goal is, because astronaut's life depends on whether this overall system is stable or not, I need to prove stability. If I don't prove stability of this system, this overall architecture, I'm going to put this overall in quotes, because as we will soon see that this system looks slightly different from the original system that we started with. So this overall system is going to be slightly different from our original system, and I need to prove that this new system is going to be stable. Okay. Any questions so far? So I'll draw the system diagram of this overall architecture. X hat t dot a x hat t plus but, and my y hat t c x hat t plus dut, and my yt is cxt plus dut. And the architecture looks something like this. This is regulation signal R of t. I have the system that's outputting y of t. I have the observer that's taking in the ut and yt, and then it outputs x hat of t that goes into the controller that then feeds back into the system. Okay, so this regulation signal is not a new signal. It's something we talked about a few weeks back. Generally speaking, regulation signal is something that is the offset that one of your colleague was talking about earlier. So when we are, say, regulating the temperature of the room, the regulation signal would be 70 degrees Fahrenheit, and everything else is happening in order to make sure that we are at 70 degrees Fahrenheit inside the room. So RT essentially corresponds to the steady state behavior or some sort of behavior that we want that particular system to have. And okay, my ut is f x hat t plus rt. This is the architecture that we have come up with. Your x hat 0 can be arbitrary, and x hat 0 is you can pick whatever your favorite x hat 0 is. Hopefully you have a good estimate of x naught, and so you can pick your x hat 0 to be whatever estimate of x naught you have. Any question on this diagram? I want to erase this diagram. Okay. Yes, please.
About the diagram. So
Yeah.
is that like some specific kind of configuration of controller? I mean, is there a name? Or I was thinking, should it be called state feedback controller?
It's not state feedback, because in state feedback you have the measurement of the entire state. So this one is
Observer-based.
observer-based controller, observer-based dynamic controller. Okay, so now the question is, what's the overall system? What is the system whose stability we want to prove? Okay, so not only we want my xt to go to 0, remember that the goal is not just xt to go to 0, but x hat t to also go to 0. Okay, So my new state is actually the overall system comprises of xt and x hat t. So what's my xt and x hat t together looks like? Oh, no, I made a mistake. Sorry. Remember, we are supposed to put this, there is supposed to be another k yt minus y hat t, right? Is it y hat t minus yt or yt minus y minus y hat? Okay. So I need to unpack everything and write it in the state space form. So that's my goal, and I'll need your help with that. So let's get ready. I want to simplify stuff. So what is this? This is axt plus bf x hat t plus brt. What about this thing? This is kc xt plus a minus kc x hat t plus dut and dut will get cancelled. What else will I be left with? Okay, and my yt is going to be cxt plus df x hat t plus brt. Did I get everything right? Did I make any mistake? Who can tell me what this matrix is going to look like? So now I'm going to compress the state, the two states, x and x hat, into a single state, 2n dimensional state. And Now I need to figure out what the system matrix for this looks like. Because remember, I want to prove stability of the feedback system. So what is x dot t equals to? A axt bf x hat t brt. What about here? X hat dot t kc Any questions so far? What can we say about the stability of this system? It's kind of difficult, right? We want to know what the eigenvalues of this matrix supposed to look like. But by looking at this matrix, I can't quite figure out what the eigenvalues of this matrix is going to look like. I don't want to worry about eigenvectors yet. I just care about the eigenvalues at this moment. I just want to prove the asymptotic stability. And I know that the asymptotic stability is determined by the eigenvalues of this particular matrix. So what should I do? I'm in 1950s. I don't have computer. I'm a graduate student at Ohio State University in 1950. University doesn't have enough money to buy a computer, so I have to do it by hand. Any ideas? So this is the key thing. Yeah, you have an idea? No? Okay.
So I was just wondering, shouldn't we have like a desired response of the system in mind, and based on that we have some poles. For example, if we want the
right, so that's A plus BF, right? A plus BF is the poles. Well, that's what we want to figure out, like what exactly are the poles of this particular system going to look like. So ideally we want to design K and F, right? Sorry?
We are designing K and F. Right?
That's right.
So shouldn't we take some pole values based on how quickly we want the system to converge and then back?
Absolutely, that's what we want to do. But first I want to get this matrix right. Okay, because then the problem might become somewhat easier. Okay, so I want to massage this system in a way that my problem becomes somewhat easier. Okay, so here is the trick. Instead of considering x hat t as my state of the system, I'm going to look at Et, which is xt minus x hat t as my state of the system. Okay, so I'm going to replace this x hat t by Et. And what is the expression for Et based on this thing here? So Et is A. So I have to subtract this from this. So I have A minus Kc. Oh, this one gets cancelled with this one gets cancelled with this one. So I have A minus Kc xt minus x hat t, which is a minus kt kc et. Okay, so now I have a problem. Wherever I wrote x hat, I need to replace x hat with xt minus et. So wherever you see x hat here, just replace it with xt minus et. And now I want to have the updated state space where I have x dot t and e dot t here on this side. So let me erase this part completely. So while I am erasing, please find out what the matrix is going to look like for x hat dot t and for e dot t. Sorry, not x hat, sorry, xt and et. By the way, this is just a similarity transform of the original system, right? Because I took the first component of the state, subtracted it from the second component of the state. So it's a similar system. It's not a different system. It's just that the state representation has changed slightly in this case. Yes.
So I was wondering, how did you get a minus kc x2 minus x hat t?
So I have to subtract.
So
Oh, sorry. This is e dot t. Yeah. This is e dot t. Yeah.
Yeah. So you subtracted x dot t with
X dot t minus x hat dot t. Just take the derivative, time derivative of these two things and subtract it. Yeah, sorry. Thanks for pointing it out. This is e dot t. We derived this equation in the previous class as well. Okay, so what is x dot t? What does x dot t look like? A plus bf minus bf What about E dot T? E dot T is A minus KC ET, and it doesn't involve X of T. Then I have B and 0. So this is what my closed loop system equation looks like. Did everybody arrive at the same expression? I think it's easy. I want you to look at this expression carefully, look at this system carefully. Can someone tell me under what conditions would this system be stable? Inherently stable. When is the A matrix inherently stable? In the absence of regulation signal. So this matrix, remember, because you have a 0 here, the eigenvalues of this matrix is the same as eigenvalues of this matrix and eigenvalues of this matrix, because we have a 0 here, right? So the eigenvectors change because of this term, but the eigenvalues actually don't change. Eigenvalues are still the eigenvalues of these two things. So this system is stable if the eigenvalues of this matrix is stable, which means it has negative real part, and the eigenvalues of this is stable, which means it has a negative real part. Okay, well, wonderful. So the theorem, this is not a theorem in the book, but it's evident from this expression. Overall system is stable if and only if A plus BF is stable and A minus KC is stable. When can we pick F so that A plus BF is stable? We studied that in the previous lectures. Either when A and B is controllable, or alternatively the uncontrollable subspace is stable. Okay. What about A minus Kc? When is A minus Kc stable? I can pick K when A and C is observable. Alternatively, the unobservable subspace is stable. Okay, the eigenvalues corresponding to unobservable subspace, they have negative real part. Okay, awesome. So as long as my system is controllable and observable, or alternatively the unobservable subspace is stable and uncontrollable subspace is stable, I can pick a gain F and an observer gain K so that my overall system is stable. What happens if overall system is stable? My error will go to 0 and my xt will also go to 0. Even in the absence of regulation signal, my x dot t will go to 0, it will be stable. So xt will also go to 0, and that's exactly what I want. I want my astronauts to go to the space. I want them to stay on the trajectory to the space, to the moon, to the Mars or whatever, and it won't be unstable. It won't crash into the ocean. It won't blow up. It won't have any of those funky behavior. Anything else that you notice? You know what else I notice here? What I notice is that my error signal is uncontrollable. My F matrix doesn't influence the evolution of the error signal. Okay. So observation or fact, F does not influence error ET. So the controller gain does not influence error ET. What does that mean? That my error is not controllable. Yeah.
Doesn't it also imply that your error, no matter what your control gains are, your observer error, which is what E represents, isn't going to change?
It's not going to change, right? So observer error will not change based on the controller design. So the controller cannot influence the observer. It's an artifact of the specific strategy that we have picked, which is linear strategy and all that, linear estimator, linear strategy. That will of course not be the case if you were doing nonlinear strategies and so on. But as far as the linear strategy, as far as you stay within the class of linear controller, so because this is 1950s, everything has to be linear because that was the technology at that point of time. So F cannot influence the error ET. In fact, ET is uncontrollable. So error is uncontrollable state. Uncontrollable state. In fact, if you look at the controllability matrix, what is the controllability matrix for this system? Let me erase this side. So the controllability matrix is B0 A plus BF B 0 A plus BF square B 0 Okay, so controllability matrix has this whole n, the bottom n rows are uniformly 0. So it is rank deficient, and therefore the controllability, it's not a controllable system. And that's what this fact essentially implies, that this system is not controllable, and the error is actually the uncontrollable state. And in fact, the only way to influence the error is by choosing your observer gain k. There's no other way through which you can influence. The controller cannot influence the dynamics of the error in this particular system. Okay, so not a fact, but a rule of thumb. We want estimator to converge faster than the controller. Faster than the control state. What that implies is we want lambda I, or real part of lambda I of A minus kc to be much lower than the real part of lambda I of A plus BF. So your observer is going to converge to the steady state much more quickly than the, and of course you want this to be less than 0. And the other fact or another observation here is F and K can be designed separately. What that means is you can pick the eigenvalues of this separately from the eigenvalues of this. F and K are not coupled in any sense. As long as you are purely concerned about the eigenvalue. If you care about the eigenvectors also, then of course they are coupled. But generally speaking, when people are designing this observer and controller system, they are generally not doing eigenvector placement. I don't know why they are not doing eigenvector placement. Maybe it's not important. I've not worked in this area to know enough about this, but as long as you're not placing the eigenvectors of this matrix, it doesn't matter. The K and F are sort of decoupled, and they can be designed completely separately. So F is designed so that this matrix is stable, K is designed so that this matrix is stable. And this idea, this notion, this observation of designing the controller separately from the observer is called the separation principle. So this is called the separation principle. This principle has become a very important part of control system design across industry. So no matter, I know a lot of people have worked on automotive systems. Automotive systems are generally nonlinear. Nonetheless, even though this theory was developed for linear systems, this idea of separation of estimator and control has been adopted across a wide range of linear as well as nonlinear systems. Because it's easy to understand. I can have one group that is focused on estimation design, I can have another group that's focused on control design, and I can enforce this separation to say that whatever the estimator's output is, I'm just going to feed that into the controller part that somebody else has designed, and hopefully that overall system is going to work. And it turns out that the overall system actually works. Like, that's how we have been to space, that's how we have been to Mars, that's how we are actually we have been to Jupiter and all sorts of exoplanets in the solar system, because this separation principle is actually a very powerful tool. Even though this was actually originally found for linear systems, without proof, people tend to use it for nonlinear systems as well, and so far it has worked wonderfully. You could have some situations where the separation principle may not yield a good result, but by and far, I think this has worked out well for most nonlinear systems. Like, I have not seen a specific situation, I have not seen any system where the separation principle doesn't work. In reality, like in theory, people can write all kinds of complicated papers, but in reality, everybody just uses the separation principle to design the controller and estimator separately, keeping this sort of constraint in mind, the fact that the estimator should converge much more quickly than the controller. Okay, any questions so far? Okay, is this idea of separation principle clear? Okay, this is the most important take-home message from this this class. Later on, you might be designing cloud systems, you might be designing satellites, you might be designing rockets, you might be designing vehicles, control system, and everywhere you will have an estimation team, you will have a controls team, they'll design their system separately, you will merge the two, and you will pray to the God that the overall system works as intended. Okay, so that brings us to the end of the syllabus for this particular class. I want to emphasize on what the sequence of thoughts in this class was. So let me just write it down. So we started with a linear system. And we were concerned about the first part, or the zeroth part, was, does a solution exist? We said that, look, this function looks like a Lipschitz function, so there exists a unique solution actually. And then we said that, okay, the unique solution actually is represented by a matrix exponential. and we talked about matrix exponential and modes of the system. So we said, okay, the solution to this particular differential equation exists. It's actually unique because the function is the right side is Lipschitz. So a unique solution exists because of some mathematician in 1800s who proved this result, that if your function is Lipschitz, then the differential equation has a solution. Then we said, okay, perfect. So a solution exists. Actually, I can represent that solution. The solution space is n-dimensional, and the way to represent that solution is using matrix exponential. And so we studied some properties of matrix exponential at that point of time. Then we said, okay, fine. I know that the solution exists. I know how to find out the solution through matrix exponential. I want to know whether my state xt is going to go to 0 or not. I want to know whether the system is stable or not. And then we talked about stability of the system. We studied multiple notions of stability: asymptotic stability, exponential stability, and just stable. And then we figured out that actually the eigenvalues of the system A gives you a lot of information about the stability of the system. We talked about Jordan form. We talked about diagonalizability of matrices, and we connected all of these different ideas into identifying whether the system is stable or not. And the most important result from the stability part was that if eigenvalues have negative real part, the system is exponentially stable. If eigenvalues have 0 part and it has a Jordan block of 1, then the system is stable but not exponentially stable. And if the eigenvalues have Jordan block more than 1, 0 eigenvalue has Jordan block more than 1, or real part of the eigenvalue is greater than 1, then the system is inherently unstable, and some of the states will go to infinity. And so if you think about supernova, what's happening in supernova, it's an unstable state, and there is some eigenvalue that's unstable in the linear system characterizing the dynamics of the supernova, and that's why it's not stable. It explodes. Then we said, fine, I have an unstable system which is inherently unstable. I have a flight, I have an airplane that's flying in the air, it is inherently unstable. If I don't control it, that flight is going to crash into the ground and people are going to die. So Wright brothers said, you know what, I need to make sure that this particular flight, like everybody has come up with uncontrolled flights so far, everybody has died, or well, not everybody, but many people have died trying to create a human powered flight. So let's try to understand how to make this uncontrollable system controllable, or the controlled system stable, because that's what everybody wants. That's the desirable property. So we came up with the notion of controllability and observability. So observability is about identifying the state of the system given the observation, and controllability is about being able to control the closed loop system in a way that the closed loop system becomes stable. So even though the open loop system may be unstable, the closed loop system is stable. And that was the core reason why Wright brothers were able to create a powered flight and became a history. They made flights controllable by putting appropriate control surfaces around an airframe. Once we did controllability and observability, then we said, okay, fine, now we know if the system is controllable or not, if the system is observable or not. I want to actually design the controller and design the observer to have desirable properties. And so we talked about controller and observer design. And in particular, we talked about two topics. One is the pole placement and eigenvector placement. So you can do pole placement, you can also do pole placement and eigenvector placement. And once we understood the controller and observer design, then we talked about the separation principle, which was today's class. So by separation principle, what we mean is that the controller and observer can be designed separately. You fuse the two, and it turns out that the closed loop system is going to be stable as long as the individual controller is stable and the observer is stable. So that was the entire train of thought. That's our entire, I think, 22 hours of lecture in 10 minutes. That's a good punchline. But yeah, so this is 22 hours of lecture in 10 minutes. And that's the train of thought that we followed in order to understand linear systems and the controller design and observer design for linear systems, which has fueled much of the growth in the controls area over the past 50 or 60 years. Okay, now what's next? In the next class, I want to go from continuous time systems to discrete time systems. So far we were talking about 1950s. We wanted to go to the space. We wanted to design controllers using linear systems theory in order to go to the space. Now, what happened in 1960s and 70s? Microprocessors and microcontrollers came into being, and fortunately or unfortunately, they are digital devices, and therefore they work with clock ticks. And because the clock ticks in a discrete fashion, they work in a discrete fashion. And so now I have a sampled system. So I have a continuous time system, but I don't have like an analog circuit controlling that particular system. I actually have a digital circuit controlling that system. So now I'm getting sampled information from this continuous time system. I'm making sampled observation. My controller is injecting signal in a sampled way with a zero order hold. So if I'm injecting fuel in my engine for the next clock tick, so from time 0 to 100 milliseconds, the amount of fuel injected or the rate of fuel injection is going to be constant. And then at 100 to 200 milliseconds, I'm going to change the amount of fuel injected. And then 200 to 300 milliseconds, I'll change the amount of fuel injected, and so on and so forth. So now my controller is also injecting signals in a sampled way with a zero order hold. So now I want to understand this funny system, which actually is continuous time. But the way we are trying to design the controller and the way we are trying to observe the system is in a discrete time manner. So how do we convert this idea that we have learned for the continuous time system into ideas for the discrete time system? So in particular, I think the solution will always exist. So we probably won't worry about the solution for the discrete time system. But we will talk about what the solutions of the system is going to look like, and it won't have matrix exponential, but it will have something along those lines. We'll talk about stability of discrete time system. We'll talk about controllability and observability of discrete time system, and then we'll talk about controller and observer design for discrete time system. Much of the tools and techniques that we have studied for this will be very useful there. So we will freely use the concepts of pole placement and eigenvector placement for discrete time system. But some of the results will be slightly different. So the modes of the system might look slightly different. The stability of the system criteria might look slightly different for discrete time. But I'll connect the two strands of thought so that you understand that what we studied for the continuous time system has a counterpart in discrete time and vice versa. So then you will become very comfortable going from continuous to discrete and discrete to continuous. So that's the goal for the next 4 classes. So we just have 4 classes left in the semester. That's the goal for the next 4 classes. You can choose to come, you can choose not to come. If nobody comes to the class, I'll cancel the class. Okay, so I don't know how much time this is going to take. Hopefully I'll be able to cover all of this stuff in the next 4 classes, and then we'll be done with the semester. So thank you so much, and I'll see you on next week, Tuesday.